to detect the cylinder position. So there is different kind of sensors for different purpose. So they could be typically for proximity sensors, right? We will look into whether it's you see there is a this sensors, right? It will measure if this sensors is for T slot or C slot. Okay, so what does it mean is that for each of our different cylinder, right, like the SPC, you have a fixed place for you to put in your sensors. So like you can put in your sensors here. So we need to know these sensors, this slot here is a T slot or C slot. So for example, T slot and C slot. So it's just look differently like where this okay, so this is something like a T slot. Maybe not. It's not a very good picture. Let's see if okay, let's just see the actual one. We will see the did you have briefing about this? The T slot, C slot?
Not yet.
Okay. Okay, so you see sensors like this is what we call as a T slot. So it does look like a T, except this is not long enough. So this is what we call as a T slot sensor. Then we have C slot like this. So you see it's a C slot. So definitely these two different slot, right? The sensor will have different because like for example the sensor we have here, this is a T slot, so it can only be put inside the T slot cylinder. So this is a C slot. So when you're selecting the sensors, you need to make sure that it's suitable to put inside. And the first thing that we normally will see is whether it's a T slot or C slot. Okay, so but then although like this is a very general way to choose it, but not necessary that all our T slot cylinder is suitable to, all our T slot sensor is suitable for all T slot cylinder. So certain cylinder, it might still not be accurate, and that's why if we look into like our just go to any sensors, like the proximity sensors, right? And you see inside because there's some order, right? There is this document inside the product information. Okay, we have this document, the right sensors for the drive. So if you look inside here, right, it will have a table to tell you, like, if let's say your cylinder is ADN12, what are the sensors that is suitable for your cylinder? Okay, so in this case, like, okay, you can use ST, DTM, SV, but you can't use SFT10M. So all these are different sensors with different technology. Like I don't have the slide telling you the difference of the sensors. I'll try to find it later. If I found it, then I'll send to you guys. But basically, they have different technology. Like in terms of connections, we have whether it's a PMP or MPN sensors. So all this is determined by the model. So in this case, like it's a MPN sensor. Then we also have PMP, and then there's a difference of like whether it's normally open, normally closed sensors. And also we do have some sensors which is like not NPN or PNP, just a standard 3-wire sensors. Also we would have 2-wire sensors. So there is a difference of all these kind of sensors. And then why we have so many sensors is actually because of the different technology, whether it's a reed switch, solid state switch, this kind of different sensors, and they have their own benefit and their own difference. But I don't remember by head. I need to look for the site and then I'll send it to you guys later on. But this is for proximity sensor, so it's mainly to use with our cylinder. Okay. Then we also have sensors for like our actuator, electric actuator. So electric sensors like depending on we have like a SIEN. This is yeah, it's also just different sensors. Basically, whether it's a PNP and PN to use together with our drive. So we could have like, for example, if we know like we want to sensors for ELGT, then we can find like here. You can find it here inside here. In terms of the position sensing, you can find like what is a suitable sensors for your electrical drive. Okay, then in terms of the sensors for this one, right, we have different kind of sensors. Is for example like ELGD, right, the sensors is metal detecting. So that means you need to install something like this. We just showed on the actual one also. It's better. Okay, so as you can see here, right, just now we talked about cylinder sensor. Cylinder sensor, right, it doesn't, normally for cylinder, you have a magnet inside the cylinder in order for you to detect detect where is the piston rod, right? But for electrical, you don't have a magnet. So these sensors for the electric actuator, right, it's metal detecting. So if let's say we have it will trigger when we put a metal over to it. You see? Yeah, it will trigger when there's a metal. So that means when you are let's say sizing the actuator, right, you will need to have this I don't know what is it thing called, but when it moves, right, so that it will detect the locations of where is the actuator right now. So you are using this metal plate here to activate the sensors. So these are all the metal detecting. So it is not detecting by magnet. But of course we have some electric actuators such as I think the ESBF. There is certain actuator that have a magnet inside as well. But most of it they do have a magnet, and which is why you need to add a metal plate here to the slider for you to detect for you to know like to activate the position sensors. Okay, yeah, so same like okay, for example this one, this is a EPCC. I think yeah, this is EPCC or EPF. In this case, right, we don't have a metal. So it's actually there's a magnet inside. So the magnet will activate the sensors. So unlike different with this one is that you need a metal plate. Okay, so that's our mainly our position sensor. Okay. So for position sensors, this kind of proximity switch is straightforward. It's just that it's just a digital input. If it's there, then you get a feedback, and if it's not there, you get a 0 or something like this. Okay. But we also have a more advanced position sensor, which is
Teaching one.
what was that called? Position sensor is a position transmitter. So something like this. So this kind of sensor is that it's not a fixed input and output. It's actually you can see it's an analog output of 4 to 20 milliamp. So it will detect like there's a certain length of it. Like for example, in this case, it's a 50 mm, right? Then you can use this on the 50 mm cylinder. That it can tell you exactly what position your cylinder is at. So it could be like by detecting the magnetic strength, right? It could be like from 0 to 50 mm. Like if let's say your cylinder is located halfway, like at 36 mm, for example, right? It will be able to tell you that your cylinder is now at 26 mm. Yeah. So that's the position transmitter. We also have it here, as you can see. Sorry, you will ask me guys to move further down. Maybe I'll just show it here that yeah, we have an SDAT here. Okay, so this SDAT is you see is showing that 50.83 mm right now. So if we retract it, right? Can I retract it? How do I retract it?
Wrong one.
Corner. What's wrong? Why? Why I can't retrace this one? Wait, is it? Yeah, I forgot where's the control for this one. It's okay. But anyway, you can see like if let's say I try to push it right now, you can see that if the position is slightly moving.
Yeah.
Yeah. So basically this will detect like if let's say your position here, okay, maybe I can try this. Yeah, you see we can okay, now it's 0. Then when I move it to middle, it will tell you exactly like what is the actual position instead of like, you know, just like our proximity sensor, right? Okay. Anyway, you get the idea. Okay. Yeah. Okay. I think I'll just go through the sensors here then. We also have the pressure sensors like this, SPAN. There's different kind of model for different usage, of course. So this is a SPAN, it will give like pressure sensors. So for the pressure sensors, there's a lot of model that you can select, whether is it like you just want a digital input, or you want it to come with analog, like 4 to 20 milliamp. Normally, if let's say for analog, right, it support analog like 4 to 20 or 0 to 10 M, right, it also support I/O link. So that means you can use it as an I/O link device. So the difference compare like for I/O link and analog is that for I/O link it's I would say you can do a lot more things because you could have if let's say you use analog, right, then you have only like 4 to 20 milliamp. Then you might not have the digital input. But for I/O link, when you get the precious input, at the same time you can get also the digital output. Like, because for pressure sensor, you could have set a lot of things like window comparator, just like this. Something like, okay, for example, if it reaches certain pressure, then it will trigger a digital output or something like that. Yeah, all these data could be get from the I/O link. And with I/O link, right, just like I mentioned, you could have used the IOSDU, so you could have do a lot of configuration directly from your PLC, you know, to change the parameter inside. Like you can change the output set point. Like maybe now it's like if you reach 5 bar, then it will trigger the output, but you can change it to 6 or 3 or whatever depending on your program. Okay, then we also have a flow meter. Yeah, I really don't know what to say about sensors, but basically we have a different sensors, and most of our sensors can be connected with IO-Link. Yeah. Okay. Okay, then. Okay, then we have the laser sensors. So these laser sensors is also, there's also different kind of laser sensors. Whether, for example, this one is just like it will trigger when it's an on-off trigger, or there, like, remember we will play the game stations, right? It actually can detect how far is the distance. Yeah. So depending on the model, some is just like on-off, and some is like can be detected sensors. But again, these are more just theory things that you guys can look at the slide or learning campus later on. So there's nothing much for you to try it out with sensors, but like what you can do later is you try to, yeah, it's connected. Yeah, I think I have some IO-Link, loose IO-Link device here that you can try to connect to the IO-Link master, then you can play around with it. Yeah. Okay, then. Okay, wait, let's go back there. I'm not sure what other sensors that we have. Okay, so. So these are the induction sensors. So mainly it's like this is used to, like, for example, when in a conveyor, right, when something is moving, then it can be used to detect if there's an object there. So yeah, it's also another sensor. I think nothing much about it. Okay, then we have pressure sensors, but if you see pressure sensor, we have a lot of kind. We have SPAN, SPAU. Okay, the difference is that you see, like, all these SPA something, right? It's all for pressure sensor for air. But if you want pressure sensor for water or liquid, then you need to look for the SPAW, the one with W. Okay. Then if you look inside the data sheet, it will actually mention that the operating medium is liquid medium. But for other sensors like SPA, SPAU, right, it will only mention that it's only for compressed air or inert gases. Okay, so for water you need to use SPAW. So same with flow, like we have for SFH, SFNE, all these are for to determine the flow rate of the compressed air or inert gases. But if you want to look for water, then you need the SFAW. Okay. Then optical sensors. Optical sensor is the one that I mentioned now. It's for the laser, so it has a much longer working range for you to detect whether the product, whether there is a product or if there is no product. But these are more straightforward. I'm not sure about these two things. Okay, so I think, yeah, that's all for sensors, to be honest. You guys can look at it yourself. But then we will go into the SMS. We will have more things to talk about SMS. Slide. Okay, so SMS is actually it's like our electrical axis. Okay, it consists of motor, it consists of actuator, and then there is a motor driver, which is the thing that this thing is like the motor driver. Okay, so the difference with our standard like CMMT solution is that this whole thing is integrated. So that means when you buy, right, you buy a SMS as a whole. It will come together with the actuator already, the motor, and with the control unit all together in one unit. Later you can look at the knowledge wall on top of on knowledge wall. We have multiple different kind of SMS there. So with SMS, right, when you purchase it, it will already fix like what type of actuator you want, how much is the length, something like this. Okay, and for SMS, you could control it with two kind of board, whether it's through digital I/O. So with digital I/O means that you can just ask it to extract. It works like a not completely like a EA drive. For EA drive, you can ask it to go to whatever position that you want with whatever speed, with whatever force, right? But for actuator, for SMS, right, you can't do that. You can only ask it to go to extract and retract like a cylinder, but instead of a air cylinder, it's an electric run cylinder. Okay, so you can only ask it to extract and retract with digital I/O. Then with I/O link, we have additional control which it can set like a third position for it to go. I think you should be mentioned in the slide as well. Let's go through the slide first. Yeah, so as you can see here, it's actually much cheaper compared to our CMMT and sample. It's slightly more expensive than
pneumatic cylinder.
The pneumatic cylinder, but it also has more functionality. Okay, so yeah, it's an alternative to pneumatic actuator. What we can do is behaving like a pneumatic cylinder. It can only go like 10 positions from A to B or B to A, just like our pneumatic cylinder. But the difference is that you could also do a pressing application with our SMS. So for example here, when we can ask it to extend to from movement from A extend to C, right? But we ask it to start the pressing process, which is the force control at B. So it will ascend until B, then it will start to change into force mode. Okay? And when it's force mode, right, you can control what is the force. So what it means here is that if let's say we reach the force already, like I see we reach the force of like maybe 30% of the force, then it will just stop at the force. It will not continue pressing over the force that you have set. Okay? Is it clear?
Yeah.
Okay. So yeah, you can control with digital I/O or I/O link. Okay, so we have different kind of models here. It's just like it's all with our the actuator that we have. So it's very easy for you to configure. You can straight away just press on the this is what we call the HMI module on the SMS, right? You can have a look. So if let's say we want to control the speed or the force level or the position, right? You can be controlled with
we're demonstrating the new simplified motion series SMS actuators from Festo. The actuator series consists of 7 electric actuator families that operate like pneumatic actuators. They can perform end-to-end positioning, or they can operate in a force mode for pressing or clamping applications. Let's take a look. This is the ERMS electric rotary. This model provides 180 degrees of rotation, which means it has integrated hard stops at 0 degrees and 180 degrees. Festo also offers a model with 90 degrees of rotation. The movement we're seeing here is on the fastest speed settings. This is the ELGS-BS ball screw linear actuator. This model is 100 millimeters long, running on its fastest speed settings. These actuators
This is
are
when they are
available in
controlling
fixed
the
stroke
digital
lengths
I/O. So
up
when
to
you on
800
off, like you
millimeters.
just move move to ascend and retract position.
And lastly, this is the ELGS-TB tooth belt linear actuator. Because it uses a tooth belt, this actuator can move up to 5 times faster than a comparable ball screw actuator. And they're available in fixed stroke lengths up to 2 meters long. In the second part of the video, we will commission the tooth belt actuator from factory settings. When SMS actuators arrive from the factory, the dynamics are set to the lowest settings, which look like this. This is the slowest speed this tooth belt actuator can move. To change the speed, we use the touch panel to access the parameters.
You can press on the button here, to adjust the speed or the
On the
force.
side of the integrated motor, there are 3 buttons used to access and modify settings. There's an edit button and 2 arrow buttons. On the top of the motor, you can see the 6 settings we can modify. Let's begin by modifying the speed. First, hold the edit button for 3 seconds to access the menu. Once in the menu, I can use the arrow buttons to navigate between the settings. Let's start by increasing the speed out, which is the speed the actuator will use to move to the out position. Click the edit button to select speed out. Then use the arrow buttons to max out the speed.
Okay, so if you notice here, right, you can see that you can control the speed,
To
but
max out the speed, click the edit button to select when to speed out.
but
Then use the arrow buttons to
yeah,
max
so
out.
each time he press, right, actually it means that the speed will increase by 10%. So how you can control is just that you can control the speed, but it's only between progressive of 10%. So you like when each time he click, right, the most lowest is 10%. So then when he click it one time, it will be 20%,
20, yeah.
then 30%. You cannot ask it to run like exactly speed that you want. Like our eardrums, we can do that, but you can't do that. Do this with the SMS. You can only ask it to 10, 20, 30, 40%. Okay.
Demo setting. We get to the demo setting,
Yeah, so
where you can test out the motion profile.
Yeah, you can go to demo and then you can just control it from here.
When done testing the movement, click the edit button to return to the menu. Then click and hold the edit button for 3 seconds to exit the menu. While in the menu, it is not possible to control the actuator via digital I/O. Next, we will set up the actuator for a pressing or clamping application. When used for clamping, the actuator moves into position, then switches to force control for the pressing operation. In my setup, I have a metal part that I will press the carriage against to simulate the pressing operation. Here, you can see the actuator moves quickly into position, then switches to force mode. After the
That's
force
what
movement is complete,
the
the
animation
PLC
shows
sends the
itself.
signal
You
to
will move to
retract
that
the
position,
actuator.
and then you will start the pressing mode. When you start pressing mode, right, it will move at a lot lower speed because it
Set
will
up
be
the
force
pressing
control
application.
by that.
Enter the menu by holding the edit button for 3 seconds. We need to modify 2 settings, force and start press. Force corresponds to the motor torque, where level 10 is the maximum motor torque, and level 1 is 10% of the maximum motor torque. In this demo, I will select force from the menu and set the value to 4. Start press is the position where pressing will begin. It's where the actuator switches from positioning to force mode. Let's
The
teach
force is
start
also
press
the same.
position.
You can control the force,
Select
but you
start
can only
press
control it by progressive of 10%, 10, 20, 30, 40.
Next, click the edit button and use the arrow buttons to jog the carriage into position. And then click the edit button to teach the start press position.
So yeah, in this case, right, you see all the settings is done by manually through the buttons. Okay, so if we are connecting with IO-Link, IO-Link master, what you could do is all these parameters you could have downloaded with the acyclic data, so you can change it while you are running, because when you are running an actual production, it's not possible, or it's not good that like every time you want to change the mode, then you go to the SMS and change it, right? So that's the benefit of IO-Link. You can change the speed, you can change the start pressing position, you can change the force, the target force, all through the IO-Link acyclic. Okay, then of course this is also by doing manually with IO-Link master, and then when you connect with the FAS, right, you could have do this configuration with your FAS also. Yeah, later you guys can give it a try. You just need the EP field bus interface. Then you connect with FAS with IO-Link master, right? Then you can connect with this, and then you could have you could have adjust it. Okay. Okay, then okay, so you see, don't ignore about the exercise first. You can follow also later on, but you can see we have two ports here. Actually, one is power and one is I/O control. Okay, so power is basically you just need to give 24 volt to power up the whole SMS, and I/O control is where you can connect the digital input output control, or you can also connect the IO-Link to control it. Okay, so one thing you must take note that for SMS, right, you must power on the power first before you connect the I/O control. Yeah, because if let's say before you give, like let's say IO-Link, right, before you establish the IO-Link control, before you give the power output to the IO-Link control, you must at least you need to have the power supply first. If not, you will have error. If let's say you give the I/O control first, only you give the power, right, then you will have an error. It's actually mentioned in the instruction manual that this is something that they may ask you. So yeah, you can do the settings. It's just exercise here. Okay, so you can try it on. Yeah, okay, so as compared to pneumatics, right, in order for a pneumatic to move, you need that many of device, and then you also need the tubing and the air preparation, but for sensors as well. So basically, if let's say you use SMS, just this whole thing could replace all the components here. It saves a lot of time for you to set up, and I would say it's easier to use also. Okay, so this is just a solution. You can control with IO-Link. Okay, so as you see this video, with IO-Link, right, we can actually achieve multiple position. Just like with digital I/O, you can only extend or retract, right? But with IO-Link, you can always use the IO-Link to because just like I mentioned, you can use IO-Link acyclic data to change the position. Then when you change the position, you could have moved it to different position.
So maximum is like 10 position from 10%.
No. Position you can be a lot.
Yeah.
For position, right, it's not like by 10% anymore. The speed and force is by 10%, but for position you can be like, for example, if your actuator length is 100 mm, you can have 100 positions. Yeah, but you cannot save the 100 position all the time. So every time you need to change your position, you need to write the new position to the SMS. Okay. Yeah. Okay. So as mentioned here just now, okay, you can have because your end position is still the same for SMS when you are using IO-Link. But the thing is, for IO-Link, you can have an intermediate position. So it's like a middle position between your end, like retract and extend. You can have additional, and then you can change this intermediate position on the fly. So you can change it like as many times as you want. Okay. So yeah, basically the function, the benefit is here. How to do it later, you guys can try it out. Then we have this is just like demo, you can give it a try. Connect with the FAS also. Yeah. Then we have some application. If let's say like our customer is using a third-party PLC, right? How to use their PLC to control our SMS. We have because the acyclic data, as I mentioned just now, is through some function block that we have. So like Siemens Rockwell, we have this function block that later on, I think we have a Siemens PLC here. So if you want to try with Siemens, you can also, but you can try with the Festo first. So to understand the idea, then you can try with like third-party PLC. Okay, so yeah, basically that's for SMS. Okay, so now I think it's more to hands-on time. I'll just prepare some. I think for SMS you can just use the CPX AP on the knowledge wall. Then you have all the device here, right? Then like